The ground moved without warning. At first, it was only a violent jolt beneath the Pacific Ocean off southern Mexico. Then, buildings began swaying hundreds of kilometers away. People rushed into streets. Drivers stopped in traffic. Phones lit up with alerts. Along the coast, authorities warned residents to move toward higher ground because the shaking had occurred beneath the sea, where a powerful rupture can sometimes send dangerous waves racing toward shore. Within minutes, attention turned from Mexico to the rest of the Pacific. The earthquake struck near the coast of Chiapas, one of the most seismically active regions on Earth. Initial estimates placed it at magnitude 7.3, strong enough to cause severe destruction if the rupture occurred beneath a dense city or close to vulnerable structures. The shaking was felt across southern Mexico and into neighboring Guatemala and El Salvador. Even Mexico City, far from the epicenter, reportedly felt the motion because the soft ground beneath the capital can amplify distant seismic waves. Videos showed frightened residents leaving buildings, damaged walls, and crowded streets filled with people waiting for the shaking to stop. A tsunami warning followed quickly for sections of the Mexican and Guatemalan coastline. For several tense hours, communities near the water were told to remain alert and avoid beaches, harbors, and low-lying coastal areas. The warning was later canceled, and early reports suggested that the earthquake had caused far less destruction than its magnitude initially made many fear. Confirmed injuries remained limited, and no widespread collapse was immediately reported. That was extraordinary news, considering the power released beneath the ocean. But the absence of catastrophic damage did not mean the danger ended when the main shaking stopped. Strong aftershocks followed. Some were powerful enough to be damaging earthquakes on their own. Structures weakened during the first rupture could become more vulnerable during later tremors. In areas with soft, water-saturated soil, another threat remained hidden underground. During intense shaking, solid-looking ground can lose its strength and begin behaving almost like a liquid. This process, called liquefaction, can cause roads to buckle, foundations to tilt, and buildings to sink, even when their walls remain mostly intact. To understand why this region is so dangerous, we have to go beneath the seafloor. Off southern Mexico, the Cocos Plate is being forced beneath the North American Plate. This process is called subduction. The plates move only a few centimeters each year, roughly as fast as fingernails grow, but their edges do not slide smoothly. They can lock together for years or decades while the movement continues. Stress builds in the surrounding rock until the fault can no longer hold it. Then the boundary slips, releasing enormous stored energy in seconds. This is not an unusual process for the region. Central America and southern Mexico have experienced repeated major earthquakes along the same plate boundary. A magnitude 8.2 earthquake struck near Chiapas in 2017, killing people, damaging communities, and generating a destructive regional tsunami. Other magnitude 7 events have occurred nearby across recent decades. The latest rupture happened close to the edge of that earlier earthquake zone, which immediately raised questions about how stress may have been redistributed through the surrounding fault system. 2 smaller earthquakes had occurred before the main shock, but they could only be identified as foreshocks afterward. That distinction matters because scientists cannot look at every small tremor and know whether something larger will follow. Most small earthquakes remain small. That is why exact earthquake prediction is still impossible. Scientists can measure faults, map strain, study ancient ruptures, and calculate long-term probabilities. They cannot reliably announce that a major earthquake will strike a particular city on a specific day and hour. Anyone making that claim is not offering established science. Yet almost immediately after the Mexico earthquake, one question began spreading across social media. Did this mean California was next? The fear is understandable. Mexico and California both sit along the Pacific Ring of Fire, a vast, horseshoe-shaped zone containing many of the world's most active faults and volcanoes. It includes Japan, Indonesia, Alaska, the Pacific Northwest, Mexico, and the western coastline of the United States. Whenever a major earthquake strikes one part of the system, people often imagine pressure traveling around the ocean like a crack spreading through glass. But the Earth does not work that simply. The earthquake near Chiapas occurred in a subduction zone, where one tectonic plate is forced beneath another. California's San Andreas Fault is primarily a transform boundary where the Pacific and North American plates slide horizontally past each other. These are different fault systems, driven by different local stresses and separated by enormous distances. There is no established scientific evidence that this Mexico earthquake directly triggered an immediate threat on the San Andreas Fault. That is the reassuring part. The unsettling part is that California already carries serious earthquake risk for reasons completely independent of Mexico. Southern California sits above a network of major faults, rather than a single clean fracture. The San Andreas, San Jacinto, and nearby systems divide and reconnect across the region. In some areas, stress can move between fault strands. Researchers study whether a rupture beginning on one fault could jump onto another, extending the size and reach of an earthquake. One especially important area lies near the junction of the San Andreas and San Jacinto fault systems. Geological evidence preserved in sediments, displaced landforms, and ancient organic material helps scientists reconstruct thousands of years of earthquake history. That record suggests that some sections of these faults have remained locked for unusually long periods. A locked fault is not an inactive fault. The plates continue moving. The surface may appear calm, but strain accumulates underground. Scientists sometimes describe certain junctions as earthquake gates because their geometry may either stop a rupture or allow it to pass from one fault into another. If a powerful earthquake crossed such a junction, the rupture could become larger than an event confined to one segment. That does not mean a cascading earthquake is about to happen. It means the possibility has to be included in realistic hazard planning. A major rupture across Southern California could affect Los Angeles, San Bernardino, Riverside, the Coachella Valley, and communities far beyond the visible fault trace. Damage would not be determined only by distance from the fault. Soil type, building age, construction quality, and infrastructure design would all shape what happened next. There is another fault system farther north that demands equal attention. The Cascadia Subduction Zone stretches from Northern California toward Oregon, Washington, and British Columbia. There, the Juan de Fuca Plate is being forced beneath North America. Cascadia is capable of producing a megathrust earthquake approaching magnitude 9, similar in basic mechanism to the devastating earthquakes that struck Japan in 2011 and the Indian Ocean in 2004. Scientists continue studying whether large ruptures across western North America can influence one another through changes in stress. In some cases, major earthquakes can trigger distant seismic activity, but that does not mean every event creates a domino effect. The important point is that California, the Pacific Northwest, and Mexico each contain dangerous fault systems that must be evaluated on their own evidence. California's most famous concern remains the southern San Andreas near the Salton Sea. Some sections have not produced a major surface rupturing earthquake for centuries. That long silence is sometimes called a seismic gap. It is tempting to think that a quiet fault is safe. Often, the opposite may be true. If a fault is locked while the plates continue moving, elastic strain can keep building until the rock finally breaks. Scientists can estimate how much motion has accumulated, but they cannot translate that into a countdown clock. A fault that has been quiet for 300 years might rupture tomorrow, decades from now, or later. The uncertainty is frustrating, but it is honest. Small earthquake swarms occasionally occur near the Salton Sea and other fault zones. These clusters attract attention because they show that the crust is active. Sometimes agencies issue temporary advisories when a swarm slightly raises the short-term probability of a larger event. Usually, that probability returns to its normal background level without a major earthquake. Swarms are reminders, not reliable predictions. Another common myth is that small earthquakes release enough pressure to prevent a larger one. The mathematics of earthquake energy shows why that is wrong. Magnitude is logarithmic. Each increase of one whole magnitude represents dramatically more energy. It would take an enormous number of small earthquakes to equal the energy released by one major rupture. Weather does not provide a prediction tool either. Earthquakes begin kilometers underground, far below the influence of a hot day, a storm, or a particular season. Claims about earthquake weather may feel convincing because people remember unusual conditions surrounding frightening events, but scientific measurements do not support the idea. Animals are also unreliable warning systems. Reports of unusual behavior before earthquakes exist, but researchers have not found a consistent pattern accurate enough to protect the public. A frightened dog or restless bird cannot tell anyone where, when, or how strongly the ground will move. The only responsible answer is that California's long-term risk is real, but no one knows the exact date of the next major earthquake. So what would the big one actually look like? Hollywood usually shows skyscrapers collapsing, highways splitting open, and California falling into the ocean. The last image is geologically impossible. The San Andreas is a sliding boundary. California is not sitting on a slab that can suddenly drop into the Pacific. The real disaster would probably be less cinematic and more complicated. During violent shaking, unsecured furniture, glass, ceiling panels, appliances, and shelves can become deadly. Gas lines may rupture and ignite fires. Water mains can break, making those fires harder to control. Bridges and overpasses may close. Electricity and communication networks can fail. Hospitals may continue standing but become overwhelmed by injuries and supply shortages. A major San Andreas scenario could affect hundreds of thousands of buildings, but only a smaller fraction would be expected to collapse completely. That does not make the event harmless. A structure can remain upright while becoming unsafe, cutting off housing for thousands of families and disrupting businesses for months. The economic shock would continue long after the shaking. Damaged highways could interrupt deliveries, broken water lines could close businesses, and power failures could halt industries. Insurance would not automatically cover every loss because homeowner policies often exclude earthquake damage unless protection was purchased. Families could discover that a house standing was too dangerous to occupy, while repair crews faced shortages of materials and workers. The human impact would be severe. Parents might be separated from children at school. Elderly residents could lose access to medicine. Neighborhoods might organize food, charging stations, transportation, and welfare checks before help arrived. Disasters expose weaknesses, but they also reveal how much survival depends on cooperation. Strong building codes matter. Fast alerts matter. Yet, in the first hours, prepared communities become the emergency system. People rely on most immediately. Ground conditions could make the shaking far worse in some neighborhoods than others. Mexico City offers one of history's clearest warnings. Much of the capital stands on the soft sediments of an ancient lake bed. During the devastating 1985 earthquake, the epicenter was far away on the Pacific coast. Yet seismic waves became amplified beneath the city. Buildings oscillated violently, thousands collapsed, and the disaster killed thousands of people. The same principle affects parts of California. Sedimentary basins around Los Angeles and other urban areas can trap and amplify seismic waves. Homes only a few kilometers apart may face very different shaking depending on the soil and rock beneath them. That is why modern hazard maps include more than fault lines. They include liquefaction zones, landslide areas, basin structures, and expected shaking intensity. Knowing whether a property sits on soft ground, near an active fault, or inside a landslide zone can be more useful than simply asking how far it is from the San Andreas. Early warning systems provide another layer of protection. When a fault ruptures, it releases different seismic waves. Fast-moving P waves usually arrive first and cause weaker motion. More destructive S waves follow. Networks such as Mexico's SASMEX and California's ShakeAlert detect the first waves and send alerts before the strongest shaking reaches locations farther away. The warning may last only seconds, but seconds can matter. People can drop beneath sturdy furniture. Trains can slow. Elevators can stop at the nearest floor. Fire station doors can open before power fails. Surgeons can pause delicate procedures. Industrial systems can shut valves and protect equipment. An early warning is not a prediction. It is confirmation that an earthquake has already begun somewhere else and that stronger shaking is traveling toward you. Preparation before that alert is even more important. Every household in an earthquake-prone region should keep water, non-perishable food, essential medicine, flashlights, batteries, and basic first aid supplies for at least 72 hours. In a major disaster, emergency crews may not reach every neighborhood immediately. Roads may be blocked, stores may close, and water systems may become unsafe. Families should choose an out-of-area contact and decide where to meet if mobile networks fail. Heavy shelves, televisions, water heaters, and appliances should be secured. Older homes, especially those built before modern seismic codes, should be evaluated for retrofitting. During shaking, the safest general instruction is simple. Drop, cover, and hold on. Get down before the motion knocks you over. Move beneath a sturdy table or desk if one is nearby. Protect your head and neck. Hold onto the shelter until the shaking stops. Running outside can expose you to falling glass, bricks, signs, and electrical lines. If you are driving, slow down and stop in a clear location away from bridges, tunnels, trees, and power lines. Stay inside the vehicle until the shaking ends. Afterward, expect aftershocks. Check for gas leaks, fire, injuries, and structural damage. Do not enter visibly damaged buildings until authorities declare them safe. Near the coast, strong or prolonged shaking may be a natural tsunami warning. Do not wait for a phone alert before moving inland or uphill. The Mexico earthquake and California's long-term danger are not one connected countdown. They are separate reminders of the same reality. The Pacific margin is active, and the ground beneath major cities is never completely still. Mexico's limited damage shows what stronger building codes, early warnings, and preparedness can accomplish. California's unresolved fault stress shows why those defenses must never be taken for granted. Earthquakes cannot be stopped. They cannot yet be scheduled or predicted with precision, but they do not have to become unimaginable surprises. The plates move slowly for years, then release their energy in seconds. Human beings have to do the opposite. We must use the quiet years to prepare for the violent moments. The ground may move without warning. What happens afterward depends on everything we do before it does.